Welcome to Physics 2212, Lab 5 by Samuel Cushman. Apologies for my voice, I'm very sick right now. For the introduction and purpose, we were to observe and collect data on a magnet falling through an aluminum foil tube to apply Faraday's laws. The models and fundamentals that we used were Faraday's law in image 1, the Biot-Savart law in image 2, Newton's laws, Ohm's law, magnetic force on a loop, image 3, and the flux of a dipole, or the derivative of flux on a dipole, image 4. The results were, in the experiment, the average was 1.22 seconds, and the code outputted 1.118 seconds. The models that we used were the magnet acted as a magnetic dipole through the aluminum foil tube, and the assumptions we used was air resistance is negligible, and gravity and magnetic forces were the only forces acting on the magnet. For the experiment, the system is magnet and tube, and surroundings are everything else. Using our phone with the magnetometer app, we found the North Pole in the magnet, and using the camera, we recorded it being dropped through the tube 5 times. The average time, again as stated, was 1.22 seconds for the experiment. For the data, we have all the trials here and the averages, and then all the data for the length and width and radius of the tube, as well as our mu from the Lab 3. As for why we can't use a ferrous tube, it would have some magnetic iron that could interfere with the falling magnet with its own induced magnetic field. The magnet would fall slower than it would in free space, and this is because the magnetic force acts opposite to the force of gravity when it falls through the aluminum tube. For the code, move to GlowScript, and if we were to go over this program, we have the physical constants, which were already given, graph initialization, creating the tube of aluminum foil, we put in our data, numerical parameters, we also put in our data here, didn't edit this. Creating the bar magnet, we added the mass and mu, inputted our equations from Lab 3, did the derivative of the flux here, and then passed all these rings for the initializations. We calculated the magnetic force on the magnet, and the F note is F grav plus F magnetic, and all the other equations. If we were to run the program, we see as the bar magnet falls through, the graph shows an acceleration here, a constant velocity here, and then another acceleration here. So the color that corresponds to clockwise is blue, and red is counterclockwise because of Lenz's law. If the dynamics of the system would change if we flipped it around, the direction of the current would just flip. The magnet would just fall the same. As far as the real-world system compared to the computational model, both are relatively close with the percent error of 9.1%. If we split the tube into more rings, that would improve the accuracy. At the beginning of the graph, as observed before, the two forces, magnetic and gravitational, are unbalanced, which means velocity is changing, and therefore there's an acceleration. In the middle, they're balanced with no acceleration, and at the end, they are again unbalanced, with gravitational force taking the majority. As for discussion and error, if the resistivity of the conductor was reduced to 0, the induced current would be greater, and the magnetic force would be greatly increased. If holes or slots were cut into the tube, the induced current would be weaker and the current would be disrupted, and as a result the magnetic force would be weaker as well. When we're talking about error, the only source of error could have been from human error with the camera, or a wrong mu value from Lab 3. Either that or a minuscule error from the negligence of air resistance. Thank you.